Hi everyone, this is Mrs. G, and today we're going to start learning how to solve trigonometric equations. So there's a number of different methods we're going to talk about over the next two lessons. So today we're going to start with one of the most basic ways that you can solve a trigonometric equation. I'm going to call it method 1, and that's to isolate and use the inverse. So our first goal here is going to be to isolate our trigonometric expression. So we want to isolate sine of x. So we know that we can do that by adding 1 and dividing by 2. So we have sine of x equals 1/2. And then we have x equals the arc sine of 1/2. So we know that due to the range of arc sine, this can only give us one value as our answer, and it would give us x equals pi over 6. However, this equation actually has an infinite number of answers. So again, this function, this step in our problem can only give us one answer, but this has an infinite number of answers. So once you have a value for x, now we have to do some critical thinking and see, well, where else could this occur? So right now, we have pi over 6. We know that sine is also equal to positive 1/2 in quadrant 2, because sine is positive in quadrant 2, and that also occurs at 5 pi over 6. So again, while arc sine can't give you this answer, it is still an answer to the equation, so we have to find it on our own. But then we know, okay, these are two answers within one rotation, but we know that in trigonometry, we can keep on rotating infinitely. So we have to find a way to name those repeating answers. So this one, the next time it's going to reoccur is 2 pi units forward or backward. So we can say one answer, we're going to say x equals pi over 6 plus 2 pi n. Remember, n is any integer, meaning it would cover every possible coterminal angle here. But then we also have to find a way to name all of the repeating angles here. So again, the next time this will repeat is 2 pi units away. So then we list a second answer, x equals 5 pi over 6, and that will repeat every full circle as well, so 2 pi n. So just to recap again, when we use our inverse functions in a step, it can only give us one answer, but we know that this is not the only answer for this equation. So we have to kind of do some critical thinking, figure out what other quadrants would work for this equation, and then describe them in a repeating manner. Okay, let's try this next example. We're going to use that same technique. We're going to isolate our function first. So we want to isolate tangent. So we can start by adding 3, and we have tangent squared of x equals 3. And so if we were trying to isolate tangent, we would take the plus or minus square root of both sides. So tangent equals the plus or minus square root of 3. Don't forget about that plus or minus. So now, we would actually set up two little separate equations here. We would have x equals the arc tangent of positive root 3, and x equals the arc tangent of negative root 3. So I want to remind you that the range of arc tangent is from negative pi over 2 to pi over 2. So this expression, or this inverse function, should only give us one angle. So this would give us pi over 3, and this would give us negative pi over 3. But we know that there's actually an infinite number of answers that would look. So now we're going to kind of sketch out what our inverse function told us and then try to place that in more quadrants. So we know that tangent is positive in quadrant 3, which is why our inverse function gives us pi over 3. But we know that the tangent is also positive in quadrant 3. So we can actually place this angle here, and this would be 4 pi over 3. And the tangent of 4 pi over 3 is also square root of 3. So again, while your inverse function can't tell you this, this angle still works for this value. So we want to find a way to include that. So you'll notice that from pi over 3 to 4 pi over 3, it's exactly pi units apart. So one way I can describe this repeating answer is I can say pi over 3 plus pi n. So that's going to repeat every pi units. So that's part of my answer. And then over here, the negative version, so our inverse function told us this angle, negative pi over 3. But we know that tangent is also negative in quadrant 2, so we could actually use this angle as well. And the tangent of 2 pi over 3 is negative root 3. So that works for the value, so it's part of our answer. And again, these are exactly pi units apart, so that's how often they're going to reoccur. So we would say x equals negative pi over 3 plus pi n. So this process is kind of similar to when we named our repeating asymptote equations. We state one answer and then how often it repeats. Okay, so at this point, I'm going to ask you to pause the video and see if you can give this problem a try, and we'll check your answer in just a few seconds. Okay, so here you can see that we isolate cosine completely, and that involves taking the plus or minus square root of both sides. And notice if you're doing the plus or minus square root of 1/2, it's actually plus or minus root 2 over 2. So if you rewrite it like this, hopefully this value looks familiar. So I created two separate equations using my inverse function. So the arc cosine of root 2 over 2 is pi over 4. The arc cosine of negative root 2 over 2 is 3 pi over 4. I want to remind you that the range of arc cosine is 0 to pi. We know that cosine is also positive again in quadrant 4, so 7 pi over 4 would be an answer. Cosine is also negative in quadrant 3, so 5 pi over 4 is also an answer. And this is kind of a unique case because it is that 45-degree angle. If you look at all four of these angles, they're all exactly pi over 2 units apart. So we can actually name this in one equation. We can actually say x equals pi over 4 plus pi over 2n. So it does help to kind of sketch out where your answers would fall, and then just ask yourself, well, what is the distance from here to here? Oh, it's 2 pi over 4, which is pi over 2. Okay, go ahead and pause the video again, and now give this one a try. Okay, let's check here. So the first thing I'm going to do after I isolate cotangent is actually going to rewrite it using my reciprocal function. So the reciprocal of -1 is -1, so it doesn't look like it changed, but it is. I just used the reciprocal of both. And so x is going to equal the arctangent of -1, which remember, arctangent, its range is from negative pi over 2 to pi over 2, so this value is negative pi over 4. But we know that tangent is also negative in quadrant 2. So the tangent of 3 pi over 4 is also -1, and you'll notice that these two angles are exactly pi units apart, so they're going to keep reoccurring if you add or subtract any value or any multiple of pi. So here is our answer. Okay, so now we're going to move on to a different strategy or a different method for solving. So sometimes you won't actually be able to isolate your function completely. So another really common thing we do with these types of problems is we actually factor them. And many of these actually look like a quadratic equation. So here, if it helps, what you can do is you can substitute. You can say, we'll substitute. You can say, let cosine of x equal y. Pick a new variable, and then you could actually rewrite it like this: 2y squared minus 7y plus 3 equals 0. And then this you should be able to factor. So here we have 2y minus 1 times y minus 3 equals 0. And from here we can actually keep solving. So we would do the zero product property. So we get y equals 1/2, y equals 3, and then remember, we're actually trying to solve for x, which is within cosine, so now we have to re-substitute. So cosine of x equals 1/2, cosine of x equals 3. Alternatively, if you don't want to substitute and you see how this is factorable, you could go straight to the factors using cosine. So you could just go straight to this step cosine of x minus 1, cosine of x minus 3 equals 0, and then you could do zero product property from there, and you would end up with these same two things. So whether you want to substitute and solve before you resubstitute, or if you just want to go straight to the factoring, either way is fine. So once you get down to here, we can use our inverse function. So x equals the arc cosine of 1/2, and x equals the arc cosine of 3. So hopefully you notice right off the bat that this is a domain error. Remember, the domain of arc cosine is between -1 and +1, so this is outside of the domain. This value, we can finish solving here. Hopefully we know the arc cosine of 1/2 is pi over 3, so we'll be in quadrant 1 because this value is positive. So remember, this is the only angle that arc cosine can give us. However, there are other angles that could work for this equation. So we now have to do some critical thinking and figure out what other angles might work. So here we have pi over 3. So we know that cosine is also positive in quadrant 4. So we know right down here that 5 pi over 3 could also work. The cosine of 5 pi over 3 is positive 1/2. So there's no consistent pattern, right? The distance from here to here is not the same as this distance, so we actually have to name them separately. So we're going to start with pi over 3, so we can say x equals pi over 3, and that's going to happen every full rotation. So we say 2 pi n, and then we say x equals 5 pi over 3 plus 2 pi n. So there you go. Again, since the distance from here to here is not the same as the distance from here to here, we do have to do two separate equations to show our answer. Okay, let's try another example together. So here we have tangent of x, sine of x, plus sine of x equals 0. So hopefully when you see this, you notice that we can factor this. There is a GCF of sine of x. So we can actually factor that out, and we get something that looks like this. From here, we can do zero product property. So sine of x equals 0, tangent of x plus 1 equals 0. And here I'm going to isolate tangent of x. And now we're ready to use our inverse functions. So x equals the arc sine of 0, and x equals the arc tangent of -1. So here, arc sine can only give us one answer, and it will be 0, right? The sine of 0 is 0. Arc tangent can also only give us one answer. Remember, the range of arc tangent is -pi/2 to pi/2. So when this value is negative, we actually have to go backwards into quadrant 4. So our value is -pi/4. So again, our inverse functions can only give us one angle as our answer, but we know there are others that work. So let's have a look at each one separately. Here's 0. So we know that sine will also return to 0 at pi, and then 2 pi, so on and so forth. So sine of pi is also 0. And you'll notice that the distance from here to here is pi, and it's the same on both sides. So we can describe that repeating answer as x equals 0 plus pi n. Or you could even just say pi n. That would be totally fine. Now, for the second part of our answer, here's -pi/4. We know that tangent is also positive or negative in quadrant 2. So we know that the tangent of 3 pi/4 is also equal to -1, so that works. And again, the distance from here to here is pi, which means this is also pi, so it repeats every pi units. So we can write this portion of our answer like this, plus pi n. And there you go. Okay, go ahead and pause the video and give this one a try. All right, let's check our answers here. So here you can factor this. It is a quadratic type equation, so you can factor this as follows, and it gives you these two factors. So you use zero product property, and then you can use your inverse functions here. So hopefully you recognize you cannot do the arc sine of 6. 6 is not within the domain of arc sine. The arc sine of 1/2 is pi over 6. We know that sine is also positive in quadrant 2. So this one is going to, there's not a common distance on this side. The distance from here to here is not the same as here to here. So you have to name each one separately and say that they're going to repeat every 2 pi, which of course is a full cycle. All right, here is the last example. So go ahead and pause the video and give this one a try. Okay. So this one, maybe you notice, we could actually factor this using difference of 2 squares. 1 is a perfect square, 4 is a perfect square, and so is cosine squared. So you can factor this as follows. Or you could, of course, do substitution as well. 1 minus 4y squared, and you can factor it from there. So here, the arc cosine of negative 1/2 is 2 pi over 3. Remember, the range of arc cosine is 0 to pi. So if this is negative, we need to be in quadrant 2. And the arc cosine of positive 1/2 is pi over 3. So these two are going to reoccur every pi units, and these two reoccur every pi unit, so we can name them separately right here. Okay, that is all for today's video. Thank you so much for watching.